for only few places only. Even some faculties also there here. So in their colleges, they can't able to make some kind of UG projects also. With the help of students, they can't able to make UG projects. So today maybe it will more helpful for to you to complete this direction. You can able to make some kind of startup or start some new era in the MEMS and NEMS. So these are the contents. So we will go for the basic introduction about the MEMS and NEMS. So then we will go broader applications of the MEMS and NEMS. Then only we can able to understood where we can able to work. And next, while we are designing any MEMS sensors, what kind of key principles we have to be applied, so that we will go. And finally, I will complete my session with giving one example. So that is, we can able to make one MEMS inertial sensor. Already I had done that I will show you that thing. So these are the today content. So let me go one by one. So coming to the introduction of the MEMS. So generally MEMS is coming from past some decades. So we can call it as the micro electromechanical system. There we can able to convert our mechanical functionality into the electrical in nature. So to measure the some kind of things, in that it can able to come as a micro sensors, micro actuators, micro electronics, microstructures. These all are together we can able to call as the MEMS. So in MEMS generally any kind of mechanical structures or mechanical functionalities, mainly in any kind of the force or any kind of the bio things, we can able to convert into the electrical in nature. So that is the main function of the MEMS. So till now we are with the MEMS only, but now again one kind of new era is going to be starting, so that we can able to call it as the nano electromechanical system. So MEMS is one kind of the broader thing. So there we can able to make different kinds of the devices. Why? Because whenever we are seeing any automation is happening, means that will be with MEMS only. Because automation means for example, if we are discussing about the driverless car, so they are all functionalities will happen with sensors only. So all sensors means it can able to involve like inertial sensor, it can able to happen with some kind of sensors. Many sensors they can able to include inside, and they can able to go some kind of the automation. So nowadays this plays major role. So anyway, so to convert the any kind of the mechanical functionality into the electrical nature. And now again one new era is started, that is the MEMS to NEMS. So MEMS is in the size of the micro to some kind of mm. So when we are going for the nano, so in nano the main disadvantage we can able to see that, so whenever we are converting the mechanical functionality into the electrical nature, we are getting very less kind of the values. So that only the one of the big challenge with us we have to be overcome to convert, or we can able to go from the MEMS to NEMS. So MEMS structure means though it can able to have the all kind of the sensors. So whatever sensors we have, not only these things. So in biomedical field, so nowadays whatever we are getting the instant kits, they all are coming under the MEMS only. And coming to the energy domain analogies, so this is the one of the important thing. So we have to be discussed, because if we want to become as a very good researcher, so where we have to be started. So especially in MEMS or NEMS, so where we have to be start, that we have to be know that. So in that, so which kind of domain we have to be choose, because initially only I have been said that, so MEMS means any kind of the other functionality we are converting into the whatever we want, that we are converting. So like that, so we have the different challenges here. So these all challenges is like a very broader things. If you want to do any kind of the research in this area, so you can able to choose the topics likewise whatever you are interested. So in that, the first one is the electrical domain. So it is mainly involves with the field of the current and all electrical parameters it will be involved. So for MEMS, this is the one of the important property. And coming to the second one, that is the chemical domain. So nowadays major research is went on biomedical only. So wherever we are seeing, whenever we are seeing the projects, mainly our projects are accepting with medical only, because that much demand is there in our India. So nowadays ICM are giving many kind of the projects. So recently I have been applied 9 crores project related to MEMS only. So the thing is, so the ICM are also mainly working with bio MEMS. So nowadays whatever kits we are seeing, instant test kits. So like we have COVID instant kits, pregnancy kits, they all are they are including with microstructures, that is happen with MEMS only. So that all domain is included with chemical domain. And coming to the mechanical, so nowadays I already said one example, whatever mechanical parameter like driverless car or any kind of the things, it will be happen with the MEMS only. So there we can able to measure inertia like acceleration, that is linear acceleration, angular acceleration like accelerometers, gyroscopes, magnetometers, like that. Whatever MEMS mechanical things is there, that is coming under the mechanical domain. In that they have the very broader thing. So if we are involving in mechanical MEMS, so that is very bigger part again. So coming to the next one, thermal. So that is coming under the, we are converting in the temperature or heat into the some kind of the electrical nature. So that is coming into the thermal domain. So that included the temperature, flow, heat, and these all parameters, it will be come under the thermal domain. So coming to the relative thing, so that is the intensity, phase, is all coming in that. So next one is the magnetic parameter, like that permittivity, flux density, so these all are coming under the so magnetic domain. So these are the different fields where we can able to work. So now some kind of MEMS are available. So nowadays most of the IITs, they have clean rooms also. So I have also completed my PhD through INUP program at IISc only. So Indian Nano User Program IISc. So there I have been fabricated the 4 sensors. So that is the inertial sensor. So likewise I have been completed. So everyone, they will stop their research at one point because of the fabrication only. Because of the fabrication only. Why? Because most of the paper they are not accepting from the journal because of you not fabricated that thing. You are not tested like that. Oh, nowadays no simulation result they are not accepting from any kind of the minimum journal also. So to fabricate, so we have the different opportunities, like we can able to apply for the INUP program, so Indian Nano User Program. There we can able to go for different levels. Previously it was there with IIT Bombay and IISc Bangalore. Nowadays it will be with IIT Madras and IIT Guwahati, and some more IITs also available that you have to be checked. So that is the INUP program 1. So that is the one way to fabricate, and another program is there. So that is a community chip. So community chip means if we want to fabricate our sensor or our device, so on one wafer it will be take more costlier. So that is, we know it will be take nearly 3 lakhs like that. Whole wafer it will be cost like that. So to fabricate our device. So community chip is one kind of the platform. So there they will call one kind of call, they will call us. So many institute, they will go there and they can able to present their designs. So their ISc professors only, they will sit and they will revise our design. If they are accepted, means all designs they will fabricate on one wafer, and they will give us whatever device we want, they will give our device like that. So likewise it will be cost very less. So I had participated in that also. So there I had fabricated nearly 4 sensors again. So same kind of sensors I have been fabricated. Likewise we have different kind of the opportunities to fabricate these MEMS or NEMS sensors. So for that, don't stop work, okay? So only till simulation. So simulation is very good thing only. There we can able to go some kind of theoretical approaches only. So but we want practical, means we need to be fabricated and we need to be characterized. Then only we can able to understand the, so what is the beauty of the MEMS. So when you enter one's clean room, then obviously maybe we can able to say that our dream will be fulfilled. So like that we can able to feel. And these are the some broad research areas. In that you can able to choose any kind of the topic so to complete your research thing. So coming to the sensing mechanisms in the MEMS. So previously I said some broader things, right? So now these are all the different kinds of the sensings where we can able to do, right? So these are the some kind of the nano titles like that. So if I want to measure the force, so I can able to work on the some kind of the some pressure sensor or inertial sensor like that. I can able to choose that thing. For example, if I want to go for some kind of the bio, so these all are coming for the bio MEMS. So these all are coming from the mechanical domain, thermal domain, radiative domain and magnetic domain. So like that many kind of the opportunities we have, so to do research. So because here I will tell you one more thing. So last September I have visited the France. So there I can able to see that. So they are metros without driver, they are running it accurately. So because that much advanced technology they have, metro trains. So here we have drive, still we are with very daily we are praying God and we are entering trying to get our lives. That is practically happening. And not giving our India is having very good kind of the resources, but we are not at all utilizing properly. So if we are utilizing properly means we are in the one of the good position compared to the old. Now we are in that direction only, but some more motivation we want in that direction. So these are the some kind of the sensing domains there we can able to work. So like force, like that, some kind of thermal, some kind of DNA, all kind of things we can able to work with. Only one domain I can able to say that. So all means research domains can together. That is a nano. Because if you are going for the some kind of VLSI means we are going for only circuit branches maximum, right? So like that we have different things. But in nano or MEMS, so all background, all domain people they can able to involve. So even ECE, even civil, mechanical, all kind of the branches they can able to together they can able to work with this nano. So that much opportunities we have for this technology. And now we will discuss about the different applications where we are using the MEMS. Then we will understand the where we can able to work in different domains also, right? So coming to the first one, so that is the consumer electronics. So nowadays our mobile, so they are having the many kind of the MEMS sensors. So whenever we are rotating mobile, as he is rotating, that is coming with the kind of the gyro and accelerometer only, right? So likewise we have the different mechanisms in our mobile phones. This all kind of things, and microphone, whatever thing we are talking with microphone, that is also one kind of the MEMS sensor only. And next pressure sensor, optical sensor. So these all are coming under the generalized. So whenever we are in daily way, we can able to see these kind of the applications. And coming to the automotive industry, so one of the initiation is started from the automotive industry is the airbag injection. So whenever any high G is happening on the cars, and automatically airbag injector has to be open, then it will be work with this MEMS only. And coming to the next pressure monitoring system, so these also happening with the help of MEMS only, inertial navigation system and fuel injection system. So these all are work with the help of MEMS only. So these many applications we can able to have where we can able to identify different kind of the MEMS sensors. And coming to the healthcare, nowadays very good hot cake kind of the research thing is the healthcare. So even actually I am working as an associate dean for international relations also. So there whenever we are talking with other country universities, so they are mainly focusing on this biomedical sensing only. So they are asking about, can you able to collaborate some kind of the project related to this. So likewise talking is happening. So nowadays this health and biomedical device having very good research. So there that we can able to call as the lab on a chip. So there we can able to go from some kind of the rapid diagnostics like a COVID-19 test, some kind of the test like a pregnancy test, all it will become like that only. And drug delivery system. So nowadays that is all one of the good thing. So there, so where pain is there, there we are can able to deliver the drug. So nowadays generally whenever we are swallowing the medicine, whenever we are taking the injection, it will went to whole body only. Yes or no? If affected part also it will be take, and non-affected part also it will be take. So due to that we can able to observe some kind of the symptoms that we can able to call as the side effects. So where problem is there, if we are injected medicine, that is the one of the good idea that is coming under the drug delivery system. And implantable devices, so to measure the blood, and previously we have the device to monitor the glucose is the, so whenever we are taking the blood sample, that is also one small MEMS device is there, we are attaching that, so giving that small blood drop on that, then we can able to check our glucose level. But nowadays that also upgraded, like if we inserted one device at our arm, then automatically it will be detect and automatically it will be give data to our mobile automatically. So likewise the upgradation is happening, and ultrasound transducers, whatever scanning things we are doing, so that all are coming under this MEMS only. So these are the very good application areas of MEMS or NEMS devices. So coming to the aerospace and defense, these also. So whatever targeting things, so whenever we are targeting the missiles or we are targeting something, so there we have to produce some kind of the proper inertia. So for the exact target, so there also we can able to go with these kind of the MEMS sensors. And so coming to the next industrial application, so in robotics, generally robotics means generally we can able to say that is embedded system, but that embedded system also should be work with our MEMS sensors only. And so environment monitoring things, so whatever we are measuring air quality, so temperature, these all are coming under that only. And vibration, pressure, so whatever industry nowadays automation is happening, that is with the help of MEMS sensors only. And coming to the telecommunication, so that we can able to call as the RF MEMS. Generally for EC background we know that, so one domain is the antenna domain. Every mobile we have the some small patch antenna, it can able to detect the signals, or it can able to transfer our signal, that we can able to call as the trans receiver. So transmitter and as well as receiver. So all signals we can able to transmit and receive in kind of the electromagnetic in nature. So that also it will be happen with the MEMS sensors only. Now energy and power, so energy harvesters, so coming to that, so now I am doing some kind of research in energy harvesters. So in energy harvesters, whatever natural energy is available, so that energy we can able to convert into the electrical in nature, and we can able to harvest that thing. So that you can able to say already solar is there, na? So solar is one part, and we can able to go with some kind of the piezo kind of thing. So if you are taking some group of piezo elements, so that piezo elements they can able to generate or harvest the energy with the help of natural energy sources. So that also be coming into MEMS only. So scientific research and industry, so automatic AFS, so whenever we need to be characterization of the things, so there also we are using MEMS only. So that AFMs and microscopes and particle detectors, there also we need some kind of the MEMS sensors only. So environmental applications like pollution monitoring, water quality sensors, these all are coming under the MEMS only. So emerging applications are the wearables, quantum computing and flexible electronics. These all are coming in the MEMS only. Now you can able to ask me question like that. So these all are we known as why again you are telling. Okay, we know, but till we are with the MEMS only, micro only. Now we need to be change our micro to nano. So that is the main objective of this. So to convert this micro to MEMS, we need to be start the work. To convert the micro to nano, we need to be start. Where we need to be start? So for that we need some kind of key principles where we have to be start our design and what kind of parameters we have to be considered. So these all things we have to be considered that we will discuss now. So these are the key design principle. Whenever we are going for the MEMS, so these principles should be more useful. So if you are working for MEMS or if you are writing any journal paper, so these all principles should be there inside of the paper. Then only we can able to say that is a very good quality paper, right? In detail I will tell you that orally we will see that which kind of the key principles are there. So in that the first one is a miniaturization, integration, energy efficient and mechanical design, sensitivity and resolution, reliability and robustness, and thermal management, scaling and reproducibility, sensing and actuation, fluid and optical. This is only for consideration of the specific application only, that is microfluidic like that applications, and packaging and interfacing and cost efficiency. So whenever you are going for any kind of the device, so these all key principles you have to be remembered, and so it will be helpful to write your paper also. So if your paper there these all key points, then you can able to justify yourself that is a good paper. Because why I am saying that all things. In simulation we are getting the result. Yes or no? In simulation we are getting the result. Yes or no? After fabrication, whole results will be changed. Why? Why?
Because that was an ideal thing, right? And it is we are in the real world. We have to consider lots of things. So in simulation we are considering the ideal things.
Ideal. That exact values we are keeping there. For example, the node. So that the fabrication node value for micro is minimum 5 nanometer we have to be maintained. But after fabrication, it should be either 5 nanometer or 4 nanometer, 3 nanometer. It will become, we don't know. Again, we have to do redo things. All we have to do that. So if we are following that things, we are the best researchers. So in that the first key principle is a scaling laws, material selection and fabrication constraints. So fabrication constraint already I said na, every fabrication they have some kind of the limit. Like we can able to say that our cadence having the different 180 nanometer technology, 90 nanometer technology. Now we are working with 9, I think so. In cadence we have maximum 9. So means that is a channel width. So that is a scaling limitation we have. Apart from that we can't able to change. Yes or no? But coming to the MEMS also like that only. So if we want to design any kind of the MEMS structure, we have to be go minimum of the 5 micrometer. So other than no professor they will accept, and no fabrication they will consider for our design. So that is 5 only. But now only I said that initially our MEMS has to convert into the NEMS. In NEMS means we have to go for nano, then how it will be possible. Then like that things we have to be studied. To do that, so we have to be consider these things. First one is the scaling laws. So how that moves is there every 2 years. Transistor size should be half, our transistors whatever we are integrating that should be double, like that we are learning. So for MEMS also we have to be do some kind of the classification and do some kind of the scaling. So there we can able to go below 5 micro. Then if we are going below 5 microns, then we can able to go for the nano also. So that is the one of the important thing. And second one is the material selection. So this is the one of the key fact. So which type of sensor you are doing, that corresponding material we have to be take. For example, I will tell you that I am making some kind of the accelerometer. So for accelerometer generally which material we can able to take means, for accelerometer is basic silicon is enough. So we can able to go with some soil mumps process, fabrication process, and there we can able to implement 3-layer device. Directly we can able to get the device, right? But some kind of the piezo kind of the sensors also available. At that type of in piezo also we have the many kind of the materials, right? So these all things where we have to be incorporate So which kind of material we have to take and which is related to the fabrication. These all key points we have to be taken. Why? Because I already informed initially about INUP program, Indian Nano User Program. So then first we have one level, next we have second level. In after that we need to submit our design. There we have to be fill one form. There we have to justify what materials you are using, why you are using that material. So that also one of the very important key point. So to make over the this MEMS into the MEMS. And fabrication concept already I explained now. So how micro is coming into the nano. So like kind of things we have to be go. So these are the first key principle where we have to be start our MEMS and NEMS. So the second one is the integration. So coming to the integration, so this also we have discussed, right? So MEMS means nano means here only one domain people not working. Yes or no? So multiple domain people they are working, right? So some MEMS devices are they have 2 to 3 parameters. Like some MEM device directly it can able to measure the linear displacement, it can able to measure the angular displacement, or some kind of integration will be there. So like that thing we can able to go with. And next one is a system on chip. So that is also integrate multiple function in one chip. Then easily we can able to miniaturize our MEMS device. In that it will become as a sensing, actuation and data processing all should come in that. So when we have the IC means direct readout output we can able to get it. And next one is the compatibility with CMOS. So whenever we are converting the mechanical functionality into the electrical nature, the first thing we have to be know that so we will get the very less electrical potential or very less value of the electrical parameters. Then we need to be process that. So we need to be get into the very good value, good electrical value. Means we have to be strengthen that value. So for that we need some kind of the electrical devices. So mainly we can able to go with some kind of the CMOS devices to convert that thing. So that also we have to be considered while we are starting the MEMS design. And energy efficient. In that the first parameter is coming as a low power consumption. Low power consumption. This obviously it is coming in everywhere. So if you are taking electrical, we are saying the power consumption. Even if you are using our mobile also, okay, daily we are working for daily. So how much time we are seeing time also I don't know. We are checking battery. So how much percentage of battery we have. So if you are in travel, we are only optimizing our power. So without using some kind of the applications, we are only optimizing the power. That is a simple matter. So whenever we are designing any kind of the sensor, we have to see that it is consuming how much power. So it should be work with very less power. And next one is the energy harvesting. So that is also it is coming like a piezoelectric, thermoelectric, photoelectric. So whenever our mechanical sensors we are converting, for example, we can able to take the force. Force we can able to convert in electrical manner in two ways. One force we can able to convert with the help of change in capacitance, or we can able to convert in the with the help of piezo material directly we can able to get the electrical value also. So capacitance means that it is coming into the passive nature. So directly if you are taking the piezo means that will be coming into the active mode. So those both principles we can able to consider. And this is one of the important key design parameter. So while we are going for the sensor, in that the first one is the elastic and plastic deformation. So I made one sensor with the help of some kind of the polymer composites. Polymer composite, some kind of the force I apply, it is working properly. Okay, it is working properly. But due to some temperature increasing, so due to some kind of the energy, so that deformation or elasticity is changes. Then automatically we can able to get exact values? No. Then we have to be take care about that. and we have to go for stress analysis, how much stress it can able to accept. So that's dynamic behavior we can able to go. So what is the maximum eigen frequency, operating frequency should be there, that we should be go with that. So these all are coming into the mechanical things. So these all key parameters we can able to go with only one software, that is the COMSOL multiphysics. Have you heard of COMSOL? Multiphysics, right?
So you did all the simulation in console only.
COMSOL only.
So how accurate you are?
How?
With the practical, how accurate you are? With
That I will show
simulation?
last. Next one is the sensitivity and resolution. So that is coming into the high signal to noise ratio. So that already we know now. So if you are measuring pressure, if you are measuring acceleration, if you are measuring the displacement, so how much sensitivity is coming? So that change of the output to input. So that how much value it is coming. So that is coming under the signal to noise ratio. And nanoscale precision. So that is coming in the some kind of the automatic phenomena. So we have to be integrate to get the accurate values. And reliability and robustness. So this is coming under the some kind of the environmental tolerance. So means if one sensor I am using in North India, it will be work like one kind of the thing. So if I am working same in South India, it will be work another way, because of maybe change of temperature, yes or no? Change of environmental things. So that also we should consider while we are designing the any kind of the MEMS or NEMS sensor. And next one is the wear and tear. So that is coming under the mechanical contact. So that I will give you one good example with electrodes. So whenever we are going for any ECG like that kind, so proper contact is necessary. So for that medical people, they are going to give some kind of the electrolyte gel. Then only some good perfect contact will come. So that is one example in that thing. So that also we should consider while we are doing that thing. And shock resistance. Any kind of the high gravitational force is occurring, some kind of high things are occurring on the sensor, how it can able to react instantly. Right? So that I will tell you that. So while we are in vehicle, so suddenly airbag has to be detected. We kept that. So generally without seat belt, when any accident is happen, it will be effect on nearly 150 G of the gravitational force. 150. With seat belt, it will be only 26 G, near to 26 to 30 G. Right? Now I made one sensor, it will be inject the airbag for only 26. But due to very less accident, 3 G only happened. Gravitational force is only 23 G. It can able to inject or not? To save life, it has to be inject, na? Yes or no? So like that thing also we have to be consider while we are going to the sensor. And thermal management, already we discussed, na? So heat management. So whenever any temperature change is coming, any light kind of things are coming, so how are sensor changing its parameters, that also we should be consider while designing this sensor. And scaling and reproducibility. So that is the scaling is coming under the fabrication. So batch fabrication. So all sensors we can able to generally fabricating in one wafer only. So whenever we are going for the fabrication, so we have to be see that reproduce means one for we can able to work for only one wafer. Hardly we can able to work for one wafer. So that is successfully completed means remaining it will become automatically with the similar process. And tolerance also. And sensing and actuation. So what is difference between sensing and actuation? Very simple. Yeah.
Physical to electrical.
Physical to
electrical, that is
electrical,
sensing.
that is the
Sensing.
sensing. Actuating? Reverse.
Convert,
Very good. That is some kind of the reverse manner. So that both should be considered while we are going for the design. And feedback system. So whenever one movable sensor is there, so for example force is happened, it will be bent like that. So after releasing of that, it should be come to original position. Other than it won't work again. Right? That we should go. And this is specially for the fluidic and optical considerations. So while we are going for the microfluidics, so we should consider the first that design channel, walls, pumping mechanism, all we can able to see. So like that, this microfluidic is like that. So if this building have very good some water pumping system. So wherever we can able to go. So in washroom we are getting some waters and drinking water facility, all they are managing perfectly. Yes or no? Okay, that is generally we can able to see that. Yes or no? In micro, if our organ are in one part of organ, it necessary some kind of medication, there we can able to place that medicine. That it is coming into the microfluidics. And coming to the optical MEMS and NEMS, so here we have to ensure the alignment, minimum alignment, optical alignment should become, or else some kind of refractions we can able to get affected. And I think final one is the packaging and interfacing. So we can easily able to say some kind of mechanical sensor, how much effort we are keeping for the fabrication, simulation fabrication, that much effort we have to be keep for packaging. Because general IC means that is transistor only, directly we are packaging like our box. Yes or no? But mechanical sensors are not like that. So we have to be exposed with mechanical functionality. So that for that we have to be carefully fabricate that kind of. So that all things it is in coming under the packaging. So that is electrical interference and form factor. These all are coming under to this thing only. And finally is the cost efficiency. So whatever thing we have, finally we are seeing for cost. Yes or no? So that also we should be carefully do that. So these are the some kind of the key features that should be there for the MEMS. So already I informed now. So whatever key features I had explained till now. So these all key features there in your research, then that it will become very good outcome, like very good research paper it can able to come, and very good practical MEM device we can able to get it. And nowadays these all key features there for MEMS. Now onwards we have to go and we need to be implement for the nano sensors, means MEMS we need to be do, right? And now we will go for some kind of the design aspects. So coming to the MEMS design, so we have the two types of the sensors. One we can able to say as a movable sensors, directly movable sensor, and next we can able to call as the rigid sensors. So it won't move but it will detect. So these two types of sensors are there. For to design these two types of sensors, what considerations we have to go, right? So first we will go for some kind of the momentum sensing. So any kind of moving sensor is there, how it should be worked. Okay, here to design any kind of the moving kind of the sensor, we have to be concentrate on three parameters only. We have to concentrate three parameters only. In that, only one important parameter is the suspension beam. Okay, many places we can able to call some kind of, we can able to call suspension beam, beam structure or cantilever beam, anything. So that only the one of the important thing. So now I will explain. Maybe I will use some kind of code here. Right. Okay, these three are the important parts for the sensor. That is the coming for the movable sensor. Okay, that is one is the suspension beam, and second one is the proof mass, and third one is the electrode. So that I will explain you. So coming to the suspension beam, okay, it only decides the, our sensor is one directional sensor, are two directional sensor, are three directional sensor, or angular sensor. Okay, the structure of suspension beam only reflects which type of sensor you are implementing. Right? So in that, first we will go with this first one directional sensor. So one directional sensing means force is coming in only one direction. That force I need to be measured. Right? So here I will use one suspension beam like this, right? So one side I will make like a fixed. Whenever we are applying some mechanical energy here, like force, so directly we will go for the force only. Then what happened? It changes its nature. So maybe
Is it a piezoelectric kind of thing?
no, I'm not telling piezo. First, generally, I'm telling how we can able to design any kind of the movable sensor. Later, we will go for the specific, right? So, how we can able to design any kind of the movable sensor. Okay, it will become as an energy harvester, or it will be coming as an accelerometer or gyroscope. Likewise, any kind of the thing how we can able to design.
Changes its position.
Position. So whenever it is changes its position, right, then automatically here I kept so two suspension beam. So this I attached with one proof mass. So proof mass means where we are applying the load, where we are applying the force. So that is there. And here I kept so two electrodes, right. So that is our basic principle only. So whenever two electrodes in parallel with a medium, that is the change of the capacitance only. Whenever force is coming down, obviously this bending nature will come, and the change of capacitance we can able to get it, and force is converted into the change of capacitance. Okay, that is one kind of the electrical parameter we can able to convert it, right? And again, whenever we releases the force, it should become its original position. That also we have to be taken. Now, this sensor is only for one directional sensor, because so it will be bending only one way. We can able to bend only in one way. So that we can able to call as the one directional sensor. And here I have the some another thing. So this is already now I explained that one directional sensor, it will be move. Okay, it will be help our proof mass to move in only one direction, either x-axis or y-axis or z. And next, coming to the 2D in nature. So same two straight line means straight suspension beams are kept in L shape. Whenever any force is coming in this direction, it can able to bend it. Okay, so whenever force is coming in this direction, this part it can able to bend it. Right? So likewise we can able to giving our proof mass to move in two directions, either x or y. So likewise we can able to design the two directional sensor. So to attach the proof mass, to change the capacitance, that we have to plan later. First we need to be plan about how our direction is moving. Okay, so these are some example. No need to go only this kind of structures. No need to go in this kind of structures. These are only to understood I am telling. So whenever you are going for design, so these should be considered. If you are going for 1D means it should be go in only one direction. Any kind of the shape you are taking, L shape, S shape, A shape, whatever shape you are taking. But you have to be considered it should be going in one direction or not. And next, that is another type. So it can able to move this direction, it can able to move this direction. Whenever Z is coming, some tilting will come, then it can able to measure some change in the Z direction also. Likewise, suspension beam only heart of the sensor. So whatever parameter we want to measure in different direction, it should be come with that one. So that is the one of the parameter, key parameter to design the sensor. And next one is the rigid sensor. Okay, already sir is asking one question. Piezo, easy piezo means. So here we are telling that this is the electrodes, means we are change the capacitance simply, right? So instead of capacitance I kept any piezo material, that force is directly converting into the electrical in nature. So this electrode means it should be change of resistance, change of capacitance or piezo also possible. Okay, so that is coming under the movable sensor. And coming to the rigid sensor, that like that we can able to call as some kind of chemical sensor. It will react with our chemical values and directly it will give the output. No need to, not necessary for the moving. No need to move. So directly it is a rigid nature. So like that, this is the completely rigid nature. So no momentum is there. Now no need to worry about the which directional sensor. Why? Because it is not at all moving. It not having any kind of the mobility, right? So some kind of materials we are taking, that material should be react with our sample. Which type of chemical sample I am working? So it should be work with that chemical sample. It should be give some kind of value, result. So electrode value. So likewise, material selection for the chemical sensor only plays major role. For all movable sensor, for change of capacitance means directly silicon we can able to take. So change of piezo means directly. So have you working MEMS or not? Maximum 90% all movable sensors with capacitance only, not with piezo. Why? Because of sensitivity. Because of sensitivity only. Capacitance MEMS having a very good sensitivity compared to the piezo MEMS. And one more thing, in piezo is active sensor only, active MEMS only, but there we can able to get very less electrical value. Sometimes we could not able to process with the electrical circuit. So that is one of the major disadvantage of that.
Sir,
Sir.
I have a question. In chemical sensor, it directly convert the chemical reaction to electrical signal, no?
No, not it will convert directly. So it will be that reaction we have to be.
Yes.
Okay. So due to that reaction we are keeping some kind of electrodes. That electrodes means, so when we are going for the bio nature, we have two types of potentials.
Yes, sir.
One is the biopotential, that will be happen with the ions. That will be happen with the ions.
Yes, sir.
So electrical means we can able to say that electrons. Okay, means here it is converting into the some kind of the ions. So there we are keeping some kind of the electrode. It should be convert ions to the electrical electrons.
Electrical.
Means ion to the electrons.
Just like example.
Contact, very good. So that is whenever we are taking ECG, we are keeping one sensor, na?
Yes, sir.
So in between we are keeping electrolyte. They are measuring the biopotential only. That is in ionic in nature. Ionic in nature. Okay, what it is doing, that sensor, it is converting our ionic potential into the biopotential into the electrical nature. So
Just like we
likewise, material is depends upon our research. Depends upon which type of chemical, means which type of sample we are taking. Is it biopsy sample, or is it some kind of virus sample, or is it some kind of another kind of the sample? Depends upon that material will change. So I am not into that research, but still I know some kind of things.
My friend is in a CS background,
Okay.
and he says to me, not a chemical reaction is convert in electrical signal. It directly convert the large form of just like a diabetic meter.
That
say-
only now I said, na.
Yes.
So
It
that is
convert
in
the,
ionic nature
electric
only.
signal, then it's converted.
Then only we can able to convert. That only I am saying.
Yes,
Na.
sir.
So no chemical thing directly can't able to convert. In between we need another thing, that is the electrode. So that's why I said here. Na. That's why I kept this one.
Yes, sir.
If
I am
I kept
also
only
from-
this, okay. If directly I am saying that this electrochemical is directly converting into that is not a thing.
Yes, sir.
So
It convert in electrical signal, then it.
yes, yes, obviously, yes,
So the
that should be there. So like that we have two types of the sensor. So that is one kind of the mobility type of sensor, and second is the rigid kind of the sensors. Okay, in any field, in mechanical field now we are saying that accelerometer, gyroscope, these all are coming under to the some kind of the movable sensor. We have to be more conscious. So I said now previously we discussed now. So to design this movable sensor, we have to be mainly focused on suspension beam structure. It should be in one directional, two directional, or three directional. For rigid sensor, no need to work that much hardly, but material selection is one of the important things. So for which material it is giving the chemical reaction is one of the important criteria. Then only we can able to get the accurate value. So whatever sir said, same we have to be carefully take care about that, right? So now I explained about the key principles. After that we completed the which type of sensors we have. So we have majorly two types of the sensors. Okay, one is the movable sensors and second one is the rigid sensors. Okay, for movable sensors, important part is
suspension beam.
Suspension beam. So how we can able to design suspension beam? Depends upon our application. So I need one directional momentum, or I need two directional, or three. Depends upon that we can able to change our structure. So I given only some few examples only there. So you can able to make your own designs. Okay. In MEMS or NEMS only we have very good beauty. Whatever we are thinking, we can able to design. In transistors not like that. So whatever channel width there, we have to be follow that. But here in this thing, beauty is whatever we are getting some idea, na, we can able to implement there, and we can able to get some kind of the result. Sometimes unknowingly we are doing some design, that also we can get very good accurate output. So that is some things are there for this method. And I have completed the complete background of MEMS and NEMS. So MEMS till in micro, now we have to be move with the MEMS. So for that I given some kind of a key principles. Please follow those key principles to convert our MEMS sensors into the NEMS sensors. And I explained about the two sensors. One is the movable, rigid. So these two things we have to be. And next I'm going for my design example. So design and simulation fabrication of the high sensitivity multi-direction inertial sensor. So inertial means it is coming under the two types of things we can able to measure. One is the linear momentum we can able to measure, and next one is the angular momentum we can able to measure. So that is coming under the accelerometer and gyroscope. So how we can able to do, we will go here. Before that we need some kind of the motivation. So which type of inertial sensor we have to design? Which type of inertial sensor we have to design? Right? Now I will tell you one example similar. This is my suspension beam again. Okay? One side is fixed. So whenever I am applying the force, what happened? It is going to bend and it will give R value. Yes or no? I designed this for 30G. Okay? Whenever 30G is coming, it will work. Yes or no? I want to design for 1G. Same structure is, same kind of the thing I can able to use for 1G. Same width, same length. What happened? It won't bend. So that flexibility we have. Yes or no? So that only initial I said, only suspension beam only plays the major role to design the sensor. Right? So here, okay, example means we need background. Na? So first one is the accelerometer which measures the linear in x, y, z direction. Gyroscope which measures the angular momentum in the rotational direction. So now these are my background for which I need to be designed. So generally I want to measure at the gravity, at the gravitational force. So that is 1G. So likewise I need to be design my suspension beam structure. And next one, so whenever we are sneezing and inhaling, that also I need to be sensed. At that time, how much gravitational force we can able to produce? That is nearly 2.9 G. So that's why we are closing our eyes now whenever we are sneezing. Maybe our eyes will come out like. And next is the roller coaster. So it is happening 3.5 to 6.3 gravitational force. Car under heavy brake, it happened 6.3 gravitational force. So by Maxwell, so it produces 9G. So if we want to target any missile, it produces nearly 30G gravitational force. So whenever car accident with the seat belt, already previously we discussed, with seat belt that is 30G it will be happen. Without seat belt, 150. So that's why airbag there also without seat belt, no use. Right? So this is my background of work to design that thing. So first we have to go for which parameter. So parameter, okay. So what size of parameter I need to take? That is 1G, 5G, 10G, 30G, like that I need to be carefully I need to be considered. For that I need some kind of background work. The inertial sensor, then next after taking that, what is our application, where I need to be implement, okay, where we can able to use the inertial sensors in automotives. And next one is the consumer domain, our mobile having the gyro accelerometers, our screen is rotating in gyro accelerometers, and industrial automations, so to target the missile, military and biomedical. So which domain I need to be measured? So that domain I need to be select. First parameter, for which gravitational force I need to be designed, and next one is for which application I need to be designed. So these two we need to be initiate first, later we can able to go for design. And here, so after that, so what we can able to go with this inertial sensor? We can able to measure linear, shock and tilt, all we can able to go with this inertial sensor. And after that we need to go for the mathematical analysis. So generally comparison is happen with our sensor is simulation and fabrication. Simulation and fabrication. If I want to know about my simulation is correct or not, that I can able to match with mathematical. So then we can able to get some kind of the similarity, so we are going in good direction or not. Right? So in that, first is a estimation of the beam constant. Okay, so here I have one structure. This is also my own structure only. So this is my proof mass. Proof mass means where we are applying a force. So this is the suspension beam structure. This is the suspension beam structure. Okay, it can able to move in x direction. Say yes or no. Okay, because of this bending, it can able to move. Why? This direction. Due to this, it can able to move. Yes or no. And next one is this curve. It can able to move in z. Even it can able to give rotational also. Right? So like that, I had designed this suspension. Okay, so this is the fixed one. Whenever any force is coming on that, it can able to rotate. So depends upon load, it can able to move it. Right? So how much momentum is coming? How much momentum is happening? Okay, how it can happen means, for example, if I am applying force, how much it is tilting, I can able to measure with the help of scale or some kind of things we can able to say. But mathematically we can able to go with basic formula only, that is change of distance is coming from the force by spring constant. And so we need to go with, so how many springs are we are taking? How many springs are we are taking? Okay. And how we are connecting that springs? Either serially we connected or parallelly we connected. Here we connected parallelly. parallelly we connected. So we are taking that our total spring constant in K1 plus K2, and finally we will get the our spring constant value K. That is the total spring constant is 2K. Here I need to apply this loss. So that is Myosotis loss. There means which kind of load we are applying and which kind of direction we are measuring. So for example, that is my bending moment, or if I am applying the one point load, or if I am applying the distributed load. Depends upon that we have these formulas of the K, and that too after applying it is moving in linear or it is moving in angular, means circularly. Depends upon that we need to take these formulas. Right? Those formulas is coming into our K value. Now what is my K value? 2K. So now I am giving that 2K over here. Now finally I will get the how much this momentum is coming for this structure. So that momentum is coming 1.88 micrometers. Okay, that is in either x, y or z direction. Momentum is coming 1.88 micrometer mathematically. Then how I can able to compare that?
Is it same in this every direction, x, y, z?
Likewise I had implemented that structure.
So that x, y and z,
Z.
1.8 micrometer, that deflection.
Deflection. Right. So that is 1.88 micrometer. Then how I can able to know that my value is correct? By simulating. Same size I am simulating with the help of console multiphysics, and I will compare with same distance is coming up. Right. So that it will be give the proofread of our work. So is we are going in correct direction or not. That is for the momentum. So that is this is the mathematical momentum. So for that structure I applied maximum of 30 G gravitational force. For 30 G mathematically I am getting 1.88 micrometers. After simulation, so I am getting 1.8 micrometers. So likewise I can able to justify my simulation parameter design is true or correct or not for linear or angular also. Right? For these all moving kind of sensors are there, na? So this we must do first. Okay, first we have to go for this constant thing. How much distance is. So in this how many kind of sensors will come? Accelerometer already now we are discussing. Gyroscope also it will become in this only. This rotating also, na? Gyroscope also come. Any other? Energy harvesters are coming. In chemical, cantilever beam structures are coming. Any other movable sensors? Okay. So whatever movable sensor, we are working with movable sensor, movable sensor, where we need to go with this analysis. Now we will go for same structure, angular momentum. Right? When gravitational force is coming into the circular direction, how we can able to do? Same, I will go for same law, Myosotis law. As per that, my spring constant value is that one. So there I am applying. So how much I am getting in angular momentum? How much we are getting? Mathematically 1.562 micrometers we are getting. Then this again I need to be compared with my simulated result. So this is mathematically I am getting the 1.562 micrometers, and here we are getting the 1 point. So likewise we can able to compare our linear and angular displacement with the help of this simple and this Myosotis laws. So that is one example I already explained. Na? So this is another kind of the beam structure. So this beam structure is like this. It can able to rotate and it will be going x direction also. So like that, same we are getting the distance, and similarly we can able to compare with our simulated result with the practical things. Here also, that is for angular. This is another type of structure. This is my proof mass. So these are the 3 suspension beams. So it depends upon that spring constant and mathematical and simulated values, and similarly comparison. And so this is another type of the design. So there we have only 3 straight. So can you guess this? It will be moving which direction? Already I given, but again I am asking. Is possible for rotation? No. Why? Because again
It is
deformation.
rigid.
Rigid. All are rigid structures.
So, 2 direction, I guess.
2 means x and y.
Y is okay.
Anyone? One only. Only one. So this is completely rigid structure. Only it will go only one. Okay. Whenever you are applying, it will be bent, and when we receive, it will be come to its original position. Yes or no? Designing already initially we discussed na. Whenever you are applying force, it will be bent. After that, it will come. It has to become its original position. Or else, only one time use. This is another type of the suspension beam structures. Here we have four suspension beams and 1 proof mass. And it will be move in which direction? Anyone? You can able to move X direction? Possible? Yes, because of if I given straight means it will be going only one. So here see, I given some kind of arc structure. So due to that, it can able to move X, it can able to move Y. Okay, it can able to move Z also. Due to this bending, it can able to come up also.
So if we remove that arc structure,
If you are giving again straight na, then it will become for again rigid structure.
but then it will move for 2 directions.
True.
This
Now
will-
it is 3 na. No. So that only I am saying initially. Only suspension beam only decides. So you are the which type of sensor? That is 1 directional sensor or 2 directional sensor or 3 directional sensor. Now I think you got one good idea on that. Yes or no? So which direction we need the movement?
Sir, what is the difference between this type of model and
Previous type of model.
Previous, yes, sir.
That is
What
the,
is
see, every time I am getting same kind of the momentum.
Yes, sir.
Same time of the distance change. Here I am getting 0.91 microns. So previous is 0.21 micrometer. Yes or no? Why I am giving these many examples? Na? So initially I said that when I am giving 30G, it will be work. It will be bent. If I am giving 1G, why? Due to of specification, length, width, thickness, it will come na. So I changed many things there, length, all depends upon that momentum is. Okay, sir. Next, cross axis, that is first parameter we completed. So whenever we started with sensor, we have to go for direction. Which direction? Accordingly, we have to design a suspension beam structure. And next one, cross axis displacement. So this also we should be considered. So I am applying force in X direction, okay, but it is moving in Y also. It is moving in Y also. Meaning here my sensor, this is fixed in nature. I am applying force here. It is bending in this direction, then whatever capacitance is change is there, it will be coming in this direction only. Due to rigidness or due to some kind of plastic deformation, so actually it has to come like this, but it is coming. What happened again? What we want, exact change of capacitance measurement, we won't get again. Okay, so that it is coming under the cross axis.
Tell me one thing. I didn't get the point.
These are my two electrodes. Here I will get the change of capacitance. So that we know na C equal to epsilon A by D. Right? So okay. So these are the two fixed suspension beams. Okay. So here I applied some force. So here I applied some force. What happened? It should be moving.
Only that side, not that side. I mean, two sides are there, no? You fixed it at the two sides.
Okay, we will say this is rigid. Now easily. This is completely rigid, means
Okay.
constant.
And
Here only I am applying the force. It has to move in this direction. Yes or no? So this is whatever we know. Yes or no? But whenever any bending is coming, exact change we won't get. Yes or no? Then while we are simulating or while we are doing mathematical parameter, we are doing only this thing. We are not considering this thing. So whenever we are going to design this thing, and the next parameter is cross axis distance. Okay, so when it is going in this direction, so any other direction it is moving or not, that also we have to be considered. Okay? So that is another thing we have to be, so that becoming as a cross axis displacement, or sometimes it can able to coming as a cross axis sensitivity also. How we can next one is the sensitivity. Initially I explained, no? So 90% movable sensor, they will work with capacitor, change of capacitance only. Piezo movable is very less because of sensitivity. Capacitive, we can able to get very good sensitivity. Then how we can able to measure the sensitivity means with this thing only. So the change, so output we are getting the change of capacitance by how much change of gravitational force we are applying. So that we can able to go for, in mathematically we know how much gravitational force we are applying, and mathematically only we know how much capacitance is changing. That we need to be done, and after that we need to be go for simulation. We need to be compare this mathematical and simulation result. Then we can able to get the how accurately we are getting this capacitance. And finally is the eigenfrequency. So all movable sensors, this is the another important key factor. So that already we know na. So while we are moving on bridge, some vibration we will get. Yes or no? Any march fasting is happening, we learned in 7th class, I think 6th class, right? Any march fasting is happening, so they will do on bridge. Why? It will be deformed, na? Maybe that much bigger also it can able to deform. Yes or no? While we are working this movable sensor, okay, we are placing in different places. Like accelerometer I can able to place in my mobile. Yes or no? So mobile I am using only in sitting position? No. Standing, by walking, or any heavy speed breakers are coming. Many places I am using. Still it has to work accurately. Yes or no? So for that we need to measure the what is the eigenvalue, where it can't able to deform. So what is the maximum deformation frequency? Okay, that also we should be carefully consider for this movable sensor. So for that the formula is F equal to spring constant by mass, and that thing if we are applying. So these all eigenfrequencies whatever designs I have been shown in previously, for that these are the eigenfrequency, means operating frequency. So this design we will discuss after the break. Okay.
Sir, actually we have a break from 11:30.
11:30. Yeah.
Yeah,
Okay.
yeah.
Okay. They informed at 11. That's why I asked.
11:30.
Yes, sir.
Okay. 11:30. Okay. No problem, sir.
Can you please continue?
Okay. Sure, sir. Till now I had explained about the mathematical analysis, right? How we can able to do. So how many kind of mathematical analysis we have to do while we are doing the sensor, while we are designing the sensor? Beam constant, we need to go for either linear or angular. So we have to go for beam constant, right? And next eigenfrequency, and next sensitivity. So these all kind we have done till now mathematically. How mathematical analysis we can able to do, that we explain. Now we will go for the simulation. So now whatever I am showing, I have done this all simulation with the help of COMSOL multiphysics only. So this design initially I explained, first design. So so this is my proof mass. This S shape is my suspension beam. So this is the rigid fixed manner. So here we have the electrodes. So here totally 8 set of electrodes I had kept. So how many electrodes we are keeping, that much of good sensitivity we can able to get. Right? So here we have the 8 parallel capacitance. Whenever any momentum happening in x direction, so we can able to get some kind of some voltage. So we can able to get the change of capacitance either x, y, z or angular also. That we will do. So in COMSOL, first we have to go for stress analysis. So how much maximum stress we can able to get it. So directly we have, for that we have the mechanical simulation and electrostatic simulation. We have to go for 2 simulations. First one is solid mechanics. There we can able to measure the stress and displacement. And next one is the electrostatic displacements. There we can able to measure the capacitance. And for this structure, so this is my stress. So stress analysis. Then this is the value of capacitance. So how much capacitance we are getting? So that is 8.78 some femtofarads. And this is the acceleration versus displacement. How much? So that is already remember or not 1.8. So mathematically we are getting 1.88 mathematically. After simulation we are getting 1.8. See, that is the 1.8. Now why I am explaining the, okay, I got one idea to design. To increase the sensitivity, I had placed 8 set of electrodes here. 8 set of electrodes. But we are getting very less value of the capacitance from each. So here I can able to see that 8.78 femto, and again very
10 to the minus 15.
15, right? Femtofarads, right? So that is very lesser value. It is not possible to go for electrical analysis. Circuit analysis is not possible that much less value of capacitance. Further, I modified my design with 4 set of electrodes. To increase the sensitivity, we can able to increase the set of electrodes itself, not a issue. But we have to check the capacitance also. So proper capacitance value we are getting or not. So till previous I am telling about the complete mechanical parameters. Now onwards it will become some kind of electrical parameters. So first 8 electrodes replaced with 4 electrodes by getting good value of the capacitance. And one more thing I want to tell you, whenever you are going for the movable sensor, go for the differential capacitance. Then we can able to get the good sensitivity. So what is meaning of normal capacitance and differential capacitance? I have only one capacitance. Whenever force is applying, the change of capacitance I can able to measure. Differential capacitance means parallelly I will keep like that. For example, momentum is happening. Here capacitance is increases. Here capacitance is decreases. The difference between these two capacitance I will consider. Then I will get the good sensitivity value.
But when you apply force, then if capacitance value changes equally, then
Now these two are equal distance only, na?
okay.
Right? Whenever I am applying in x direction, what happened? This will increase, this will decrease. We can able to get less thing. Then difference of these two we will take, then we will get the capacitance value in x direction. Y direction means these two we can able to take. Z means if all 4 is changing, but that is not coming in differential again. Okay. In x, y we can able to get the differential capacitance. Whenever we are getting the differential capacitance, then only we can able to get the good capacitor sensitive value. So that also I will show you. Right? So maximum I had applied 30 G only. I work for the high G only, so that for either car back or missile targeting. So for set 1, set 2, set 3, 4 set of electrodes there. When I given acceleration in x direction, so these two I can able to get the capacitance value. The change these two. Yes or no? So if I am getting the y means again 2 is changing. Z means all will we can able to get the change. If I am getting the Z means see all 4 is changing. If I am going for only x, only 2 values are changing, 2 capacitance. So that I will consider as a differential capacitor. See, so here I am getting the 0.32, here I am getting the 0.09 because one is increasing, one is going to be decreases. This is for y and this is similarly for z. Z means all it is changing. But z I am not getting the differential. For that what I should do? I have to implement any kind of new idea. For z I can't able to get, I will get the capacitor sensitivity not accurate. So for that, if you are analyzing any kind of this thing, go for only differential capacitors. That are the first design. And previously I given mathematical analysis for again 4 designs. Have you remembered or not? One for the simple arc shape design, and second one is the 3 arc shapes, and third one is the straight rigid nature. Already I asked one question, and these are the 4. Okay, the size of this is the 500 by 500 micrometers only. Why I made this 4 sensor means I want to compare, depends upon size, depends upon electrodes, depends upon the differential capacitance, how much sensitivity values are changing, how much sensitivity value is changing, how much spring constant is changing. All things I want to be compared. So that's why I started with 4 parallel designs at same time. Right? This is a suspension beam. This is a fixed. Okay. This is my proof mass. I am applying force on that, and it can able to move. So This is the change of capacitance I can able to get from comb structure. And one more important, in previous design I didn't kept combs. We are not having any comb structure, only parallel thing is there. Then now I am explaining with comb. That difference also we need to know. Why? Because initially I used 8 set of electrodes. No? For that how much capacitance I am getting? Very less capacitance. No? Is it not at all useful capacitance? Yes or no? For that I have been changed that 8 to 4 to get the good capacitance. Still I want again very good value of capacitance. So here what we have missed means we left this area. We left this area. So if I am utilizing this area, then obviously again capacitance will increase. See, you take only these 2 parallel plates, come with this same kind of parallel plates. Now this area is covered or not? Previously I left this area, now this area also covered with our silicon. Now my capacitance value again increase or not? So that is the effective use of the material and effective use of the area. That we have to be remembered while we are designing the sensor. These are the different 4 parallel sensor. All 4 parallel sensors with the same size only, but the difference is this one only. Here we have one disadvantage. Anyone can identify? No momentum. Okay, x direction, y direction, I am not asking that, but we have some kind of disadvantage. And you can able to compare with besides. Okay, can compare with this again this all of same. Same size only, ma'am, but because of structure it is changed. Very simple. This proof mass is with only one suspension beam supported. Okay, I am telling now, if I am using my mobile while walking, while traveling, all at every time same kind of gravitation force will come. No, na? Yes or no? So here, for small gravitational force it is okay. Any high gravitational force is coming, it will be bent like this and it will deform these combs. That is the disadvantage there. Okay. So I can able to go one good structure only, but we need comparison. Why some structures are not coming effectively. So that's why I am explaining everything here. So due to that disadvantage, okay, so maybe it can able to go damage. It can get damaged. Here we can able to say same structure. Here we have one support. Here we have one support. Here we have one support. Maybe it can able to get any kind of damage. Very less. Very less because of it has good support. Okay. Whenever we are giving good support, again one disadvantage will come. What happened? Flexibility will reduce. Flexibility means it should move, na? That again it will come some kind of the momentum effect. So for that what we have to do? Here see width, here see width, to compensate that. Right. So here why I kept this one also, no? It can able to move x direction flexibly, y direction also flexibly. circular also flexibly. Okay? Here, only one. And these three having again one disadvantage. What is that? Capacitive sensitivity. Because of no differential capacitance. Only change of capacitance. So whenever we are getting the differential capacitance, then only you can able to get the good sensitivity. Then all these three disadvantages I overcome by designing this. Yes or no? So here we have the 4 electrodes, okay, and 4 suspension beam. These 4 are fixed. It can able to move X direction, then we can able to get the differential capacitance. Y direction again differential capacitance. Z normal capacitance only we can able to get. And this is our final piece. Right? Now my final question is, I am telling this is my final structure. Na? Before only I explained one structure, this one. Right? I want to ask you why I went for the another design. Understood or not? So this is, I started with 8 electrodes. Because of capacitance I moved with only 4 capacitance. Right? Now I left the design, again I compare these 3. Okay, finally I concluded this is my best design. Then now you can compare this design and this design. What is the difference? First design, this 5th design, having good capacitive sensitivity, yes. Flexibility, X direction, Y direction, Z direction, yes. Both are good only. But the comparison is fabrication. Final thing that only, na? The comparison is fabrication. See, this is my fixed. This is my substrate. These 4 electrons on substrate only. This is completely separate structure in middle. It can't able to fix it. For example, if you fabricated this, na, it will come out from the wafer. This complete part, it will come out from the wafer. What is disadvantage? See, this one 5th design is same working, but the difference again came as a fabrication issue. That we resolve with this. So on wafer only, these all electrodes will be fixed. Then this is in air also no problem, because of this 4 support is there from wafer. Understood? So these are the 5 designs. Why I explained means comparison. Started with one design. After that I compared with the different parameters electrically. And 1 to 5, why I shifted from 1 to 5. So these all parameters. Why I am telling these many things, na? If I am telling only this design today, I can able to tell that okay, my design is very effective, this thing, that thing. Okay, that is one good thing only. But if I compare, now if you are designing anything, these all matter, it will be come to your brain. Then easily you can able to go with a new kind of the designs. Understood? So these are the simulation things. See, first disadvantage I explained, maybe in stress analysis it can able to deform, sir. Right? Whenever we are going the stress analysis, we should get our complete proof mass in this color. Then we can able to say equal momentum. Here we are getting equally the change of color. So here we are getting completely some red color, and what is momentum is there, that will be happen with this flexibility. This is in equality is there here everywhere. So means not equality, one process is there. like that. So like that it is moving. So here we can able to see here. Initially it's a disadvantage, it can able to get deformed, sir. See, after stress analysis it happened already. Here I said this is also good design, because here we not having any other support, only this is the support. Due to that we are not getting good stress analysis here. So here equally we can see, again we are getting very good stress analysis, but here we are not getting differential capacitance. This is only for one direction. We are saying that more stiffness is there. Due to that stiffness, if I am applying 30G also, it can't able to move. Maybe here I can able to apply 150G, then only it can able to get it. So this is my final design. So for all these are the displacement analysis, so graphically and comparison. So comparison is happened with many existing sensors only. So finally these are totally 6 proposed sensors. One is 8 set of electrodes, one is 4 set of electrodes. This is single comb with single suspension beam, single comb with 3 suspension beams, straight suspension beams, and these are the final 4 suspension beams with combs. So this is the different direction of sensing, and this is the capacitive sensitivity. And see, whenever we are going for the capacitive sensitivity, here we are getting very good because of a differential capacitance. This is all, these two also differential capacitances only, but these are not differential capacitance. That is only the matter. So these are the some kind of the design issues. Now we will move for the fabrications. So now we started with the basic MEMS. After that we discussed the basic key principles. So while we have to write paper, journal paper, or while we have to design a sensor, that key factors are important. After that, mathematical analysis and simulation completed. Now fabrication. To go fabrication for MEMS, especially MEMS, we have mainly different types of the fabrications. In that, the first one is the SOI MEMS fabrication. Silicon on SOI micro machining. SOI micro machining process. And the second one is the piezo MEMS. Piezo micro machining. So these two are for the movable sensors only. First one for capacitive sensors and second one for piezo sensors. Okay. Then what is difference from the normal fabrication and the separate fabrication? So normal fabrications, we are starting from wafer. On that we are depositing layer by layer, we are etching. Again we are depositing, again we are etching. Like that final design we will get. But in SOI MEMS, already the predefined 3-layered wafer will available. 3-layered wafer is available. Silicon substrate, very thicker, oxide layer on the device layer with a maximum of 25 micrometers thickness. Then this substrate is constant. Whatever design we want, that we can able to go with that top layer. Then maximum of steps we can able to reduce while going for the SOI MEMS process. Maybe in VLSI we learning that in a CMOS fabrication. Startingly we are discussing with N-well process. Sorry, NMOS, PMOS. After that CMOS. CMOS we have N-well, P-well, twin tub. After that SOI MEMS we are discussing. Sorry, SOI fabrication. There we are saying. There are also 3-layer device only. So this also similarly we are fabricating. And to go for fabrication, so we need to create the GDS files. But COMSOL multiphysics won't give any GDS file. No, COMSOL multiphysics only for simulation. COMSOL multiphysics only for simulation. So here, if we want to be fabricate, we need to go for different free available softwares are there. So maybe we are utilizing Clevin software. There we are doing the fabrication. So there we are generating the GDS file. So we have used as a SOE mumps process. So how it will be there, we will see. This is the SOE mumps process. Generally, this is the predefined layer, but this is after fabrication thing. This is the bottom substrate that that is base is 400 micrometer and upside layer with 1 micrometer. Device layer is varying, depends upon that. It will be start with 10, 15, 20, 25 also available. Depends upon our requirement, we can able to get it. So here we can able to go with some kind of the process and finally we will get our device. Okay. So whatever empty thing is there we are etched, after etched we are getting like that structure. And whatever design we have, correspondingly we can able to get that kind of etching. And one thing I forgot, one more software I want to introduce. Whatever designs I explained, that is some different diagram is there. This is again some different is there. So this I had simulated in Coventerware. There is also one kind of software. There we can able to simulate the all sensors. So Coventerware. The advantage of Coventerware is it will whenever we are designing, directly it will be shown like a fabricated design. See, this is my substrate top layer.
So is it a commercial software or free?
Commercial only, not freeware. Compared to console, Coventerware is costly. And so these are the GDS 2 files using Clevin I had generated. So all whatever 4 designs I started. So for that 4 designs, that red color is our device layer, and whatever blue color is there, that is our metal layer, and whatever gray color is there, what part I need to etch, that is the thing. So this, if we are submitting to the fabrication unit, they will give we will get this kind of devices. So all 4 devices. And I initially explained one thing now. So we have many opportunity of the fabrication. In that, one is the INUP program, Indian Nano User Program. So I attended that, and one more is the community chip. So these 4 designs I went for the community chip. They will give only one wafer. They will call for that. If possible, I will inform later when the call is coming, if I am in group. So this is one wafer. So all over India, many institutes we have to be present our design. So some IIC professors, they will sit here. They will conclude that thing, that is good or not. They will analyze that thing. If that design is suitable, they will ask to how much size of wafer you want. So I asked for this size. They given this size, and these remaining are the other colleges, other university sensors.
For community chip, if you have to provide 4 devices, then how much cost they are charging?
Now I am coming for that one. If I am going for wafer, it will cost around 2.5 lakh like that, 2.5 to 3 lakhs like that it will be there. For these 4 devices, 2000 by 2000 micrometers I used. So for that, it costed around 19,600 for 4 sensors. By taking whole wafer, by keeping 2.5 lakh, 3 lakh, it is more costlier. Through INUP program, no issue. They only support a complete thing. So my design, another design I went for that only. But here, to taking whole wafer, it is more costly. So here, likewise, community way we are going means easily we can able to fabricate. For that, we have one website. Please follow ISSS community. ISSS. Like this is IEEE like that, but it's the ISSS. They are also from ISC only. So if you are taking membership, So they will inform us when they are starting this community chip. There we can able to reserve our size and we can able to produce our designs easily. Because here the final issue is fabrication only. We are simulating n number of designs. We are mathematically doing n number of designs. While coming fabrication, all whole over work will stop. So whenever we are thinking that we are in IISc or we are IITs or we are IIITs, then only we can able to do research. But if you are in other place also, you can able to use this kind of opportunities. Then with less cost, you can able to get best device, better devices.
So what is the wafer you used for this?
Soy mumps only.
fabrication?
Soy mumps only. SY.
I mean silicon wafer or some?
Silicon wafer only. So that remaining is other university device. That is some kind of actuators are there, some kind of resonators are there, some kind of micro grippers are there. I think this is micro gripper from some another kind of university. So like that we can able to use it. And finally characterization. So after fabrication, the next step is the characterization. After that, final step is the packaging, right? So for a movable or inertial sensor, so now I am given example on inertial sensor. For inertial sensor, we need to go for 3 devices. One is SEM. So by using SEM, we can able to check the how our design is coming. That is microscope image. So this is the first design and this is the second design after fabrication. This is one third one. So this is my final design. For comparison purpose only, especially I designed these 4 recently. Right? So these are the SEM result, and after that we have the microsystem analyzer. By using microsystem analyzer, we can able to get eigenfrequency and stress analysis. Eigenfrequency and maximum displacement analysis we can able to do with the microsystem analyzer, and DC, with the help of DC probe station, we can able to measure the capacitance. Right? Then where we will get this? So with community chip I made. Then where I need to be go for characterization? So nowadays all IITs they are offering. So we have to be give our result, or we need to be register through INUP portal only. They will allocate our slot. If you are sending sample itself, they are doing that. But if you want to go and complete, we can able to go there. So like that, now I given SEM images, they only given directly, but I need to be characterize and compare these things practically. That not happening. So whenever it happening, maybe we will see how much accurately I am getting that comparison. So that micro analyzer DC probe station, about that thing, what I can able to do with. For micro analyzer, we can able to go for in plane motion, means all mobile displacements I can able to measure with eigenfrequencies, and DC probe station I can able to go for CV characterization, and SEM I can able to get the accurate images. And these are the fabricated devices. So see, initially I given 1 point also na. Whenever we fabricate, simulated, whatever result we are getting, after fabrication it will change. Completely it will change. Because for MEMS, still we are minimum size is 5 microns only. I use it that only, 5 micron thickness minimum. But after fabrication, how much I am getting? 4.52. Now I can able to compare with simulation. Not possible. Again I need to go for again simulation, then only I can able to compare. So these are some differences initially I had taken. So this is about the different opportunities. So whatever opportunities we have, and what is meaning of MEMS, how we can able to go for MEMS to NEMS, and key factors, and one practical design example. So all we covered. So if you have any doubt, you can able to ask. Hope this is useful for you.
during fabrication, like actually, there are the different kind of the environmental effects are there. Like
Yes,
the humidity, pressure, and like the atmospheric, you can say the pressure and the other things are factors. So, did you consider all these things at your simulation part, sir?
yes, sir.
Did you consider all these?
We have to be considered. That only initially I said, sir. Maybe you are not there.
Okay.
Initially I explained that all key factors also.
Okay, you have considered.
Yes, sir. So we have to consider temperature and all kind of involved effects.
Pressures and humidity.
Pressure, those all things.
The fabrication using only lithographic process, right? Lithography.
E-beam.
Electron beam.
Electron.
I thought like photolithography. you were
No. If I am doing again photolithography now I am getting 6 micron, and maybe I will get 2 to 3 micron only. So E-beam is very accurate.
Yeah.
Sir, actually for the cantilever designing, did you use these names?
Yes, sir.
Cantilever designing.
Cantilevers.
So, what kind of the different structures you can propose for the cantilever?
That is depends upon which type of sample we are taking, sir. So actually I work with COVID-19. So whenever COVID-19 is there, I want to fabricate. Already IIC they made one kit also, sir.
Yeah, there is the IIT Bombay has been
IIT
actively
Bombay,
working
yes,
in
yes,
the
sir.
cantilever structure.
That is depends upon that virus mass and depends upon structure. For example, my virus is like that, sir. Just example only. So this is my fixed thing. So here I made 2 cantilevers B. So whenever this virus is coming over that, it has to fit like this only.
Okay. In this area.
In this area. Like that I need to be make this design. So means the design it should become like whatever shape of the virus or shape of the particle or shape of the sample is there, along with that we need to be go for.
But the particular area exposure is also difficult
Yes,
to
sir.
make this cantilevers.
So that's why, sir, all instant kits, medical kits are not working properly.
Yeah.
So depends upon whatever sample, and sometimes we can able to detect COVID positive. Sometimes we do not detect
Not
because of we are not properly using.
Because designing is very difficult. So,
Yes, sir,
is
that-
there any suggestion from your side how we can get some accurate kind of design? Any suggestions?
That only I explained, sir. So to design anything, so now I compared many things. So in all comparison, I got it finally one design. So if we started with one problem we will get, sir. Obviously we will get. So we have to enhancing means again one more problem we will get. So finally to design especially cantilever beams, sir. So identification of mass is important, one parameter, and suspension beam structure is one important. If you are considering these two properly, then easily we can able to get the good structures, sir.
But instrument should be so that much accurate, correct? The practical instrument should be that much accurate so that
And
it can,
again this
it can
fabrication,
deposit the
finally.
actual area actually.
Yes, sir. Fabrication also important.
Because
And,
yeah.
I simulated completely whatever sir now said. I went for photolithography. Again it will spoil completely.
That's
Which kind of resist you use for this? Which kind of resist you use for this? I mean this fabrication resist.
Generally,
That PMMA or some S1.
no, we won't go that many steps. Sorry, ma'am.
Yeah, that's what I'm asking.
No need to go that many steps. For a soy mumps only.
You did electron beam lithography, right?
Yes.
So you just coat the resist first, na? So what kind of resist do you use? That's what I'm asking.
Oxide layer. Okay. Which type of photoresist material?
Yeah, that's what I'm
Okay.
asking.
For the masking purpose.
Masking
Which
purpose.
photoresist you are using?
That is
That is the
positive.
question I think.
Positive only. Negative photoresist material.
Negative.
Negative.
So you use, I guess, PM.
Yes. Thank you.
Okay.
Thank you, sir. Thank you for giving me this good opportunity.
Thank you. Thanks for your advice.
Thank you, sir. It is indeed our privilege to be here today to with us such a remarkable session. I would like to take a moment to express our deepest gratitude to our truly distinguished speaker, Dr. Mohammed Sir, whose expertise and dedication have enlightened us all today. I now request Dr. Manoj Kumar Majumdar sir to present speaker Mohammed Sir with a certificate of appreciation and momentum.
Please, sir. Thank you, sir, for being here.
I now invite all the participants for a group photo with sir.
Thanks. Thank you, sir. Please, all of you can here. So group photo. Sir, please. थोड़ा सा कमल कहाँ पर है? बाहर Sir, please come.